Well, thank you all for joining us tonight. My name is Heather Knoll, and I am the program coordinator at Sustainable Woodstock. Founded in 2009, Sustainable Woodstock is a not-for-profit community and environmental action and education organization. We exist to lead our communities through the climate emergency, empowering Woodstock and the rest of the Upper Valley to meet climate commitments and live sustainably through advocacy, education, and collaboration. And this event is a part of our Green Drinks series. Green Drinks are social events to connect people who have similar interests. We invite local nonprofits, businesses, and individuals to make a short presentation to share their sustainability and green initiatives in our area. And our next event coming up is a film screening of Common Ground. That is next week beginning on July 24th, which is a really just lovely, positive film. Highly recommend it. And I hope you guys can join us for that. Now I am delighted to welcome our speaker this evening. Dr. Erich Osterberg is an associate professor of earth science at Dartmouth, who studies how Earth's climate system and glaciers responded to natural climate changes in the past, and how they are responding to human-caused climate change today. In addition to his research and teaching at Dartmouth, Erich is the chair of the Upper Valley Climate Adaptation Workgroup, a group of municipal, nonprofit, governmental, business, and academic leaders working to increase community resilience to climate change. Thank you so much for joining us, Erich.
Thanks so much, Heather. I'm really happy to be here. Thanks for the invitation. It's nice to virtually meet you all, and thanks for spending some time here on this first lovely evening we've had in a little while, where the humidity has given up a little bit. Can everybody see my screen? Can I get a thumbs up that you can see the shared screen? Awesome. Thanks, Heather. Okay, so what I want to talk about today is what the kinds of things that happen in the Arctic that impact us right here in northern New England. And this picture gives you a sense of where we're going for part of this talk, which what I'm showing here is a picture of a lake, which is actually on top of the Greenland Ice Sheet. So beneath this kayak is about a mile of ice, which is at the bottom of that ice is land of Greenland. But you're on top of the Greenland Ice Sheet, and every summer you get surface melting of the snow and ice, and it makes these lakes. And you can see that where the kayak is, it's actually particularly dark colored water. You can see the lighter, shallower water in the ice underneath. But this is really dark because this water bores down all the way to the bottom of the ice sheet. And eventually it can bore a tunnel all the way to the ocean and then catastrophically drain out into the ocean. And that's one of the ways that what happens in the Arctic doesn't stay in the Arctic, but we'll talk about a couple others as we go through here. All right, so just to make sure we're all on the same page, I don't think I need to go over this with this particular group, but just to be clear, we're all on the same page. Here's global average surface temperature for the last 140 some odd years, 1880 on the left, today on the right, and we can see how much the Earth has warmed in this time period, about 2 degrees Fahrenheit. And just to be clear, since about 1960, all of this warming that we've seen is from human activities, all of it. And just remind yourself really how remarkable 2015 was, which is this big jump here, and then 2016, and then we had these series of years since 2016, and then again, just how remarkable 2023 was in moving this trend upwards. And I can say that this is all from human activities, not some combination of natural and human. This is all from human activities, because without human activities, we should actually be getting cooler. Very, very slightly, but just a little bit cooler since about 1950. And we can say that because we know the kinds of things that make the climate warmer and the kinds of things that make the climate cooler, both naturally and from human activities. And the only natural thing that could affect our temperature this way would be the strength of the sun. And the sun has actually been getting a little bit weaker since around 1950. And so if you run our very latest and greatest global climate models with no human activities, that's this sort of teal colored line down here, you can see that it's basically flat for the last century or so, in a little bit of a declining trend. Versus when we run our models with all the human activities included, we get the tan line, and then we can see how well that matches what's actually happened, which is the black line. So this tells us two things. One, the climate models actually do a pretty darn good job of reproducing what's happened, and that gives us some confidence that they do a pretty good job looking to the future. And two, without human activities, there would be no global warming. Just to make it clear that you're not going crazy, this has been a particularly warm last few months, but particularly warm summer. I pulled just today the latest data for Hanover, New Hampshire from the National Weather Service. And this is a bit complicated looking plot, but on the left here is January 1. On the right is a couple days ago. And so the actual temperature on those days is this blue line going up and down, up and down. The sort of beige background, those are the normal high temperatures and normal low temperature envelope for each day. You can then see the record highs is this red line. So the record high for each day since January 1 is this red line. And the record low for each night since January 1 is this blue line. So you can see the records and you can see what's actually happened and you can see the normal range. So a couple things. One, this blue line is well above the normal range. As we went through the late winter, February into early March, you can see there were 5 new daily records set for Hanover. 4 of them were in late February, early March. And then we had another one here in mid-June. December through February was the #1 warmest on record going back to the 1880s here in this whole region, not just for Hanover, but this whole region. And May through June has been the #1 warmest. And July seems like it's going to follow suit once those data come out in a few weeks. Okay, so 3 different ways that the Arctic affects things here in New England. The first is, as I've implied with these images, we've got melting ice in the Arctic, and that raises sea level, and that raises global sea level. It's not the same everywhere. Some places sea level rises faster than in others because of what the land is doing. But in general, melting ice in the poles raises sea level. 2, perhaps not as obviously, it's possible, and this has been talked about a lot, both in the scientific literature and more in the media, that melting snow in the Arctic might actually change the jet stream. And the jet stream is actually super important for us here in New England because we tend to hang around the jet stream. The jet stream tends to be right around our latitude. And our storms, our daily weather is really strongly impacted by whether the jet stream is north of us, south of us, or on top of us, and how big the waves in the jet stream are. The third way is, as the Arctic warms, this permanently frozen area that we call permafrost is thawing. And there's a lot of carbon stored in that permafrost. And as it thaws, there is concerns that a lot of that CO2 that was locked in this permafrost is going into the atmosphere. And it's in the atmosphere that it affects global temperatures, right? So today, I just want to talk about these first 2. I'm not going to talk about the melting permafrost for a couple of reasons. You may have heard, like Bill McKibben talks about this quite a bit. I'm not going to talk about the permafrost, 1, because I'm not a permafrost expert, and it turns out that this is super, super complex. And 2, it's really not clear which way this is going to go. It is clear there's a lot of carbon in the permafrost, but as you thaw it out, other things happen. The animals and the bugs and the microbes get more active as well, and they actually suck up some of the carbon. So it's not as straightforward as one might think. But we have been doing research in my lab group on these first 2 things. And so I do feel like I can speak about where the latest and greatest science is on these first 2 issues. So that's what we'll talk about today. All right, I want to start just by taking you to Central Alaska, Denali National Park, to show you how we actually collect ice cores to do a lot of this research. So this is an image of one of our drill sites on a mountain right next to Denali. This is Mount Hunter. And in order to get to this mountain site, we have to acclimatize. You have to get your body used to the altitude before you jump onto a helicopter and quickly get brought up to the drill site with all the gear. So you can see the team here getting deposited on the drill site. You can see a lot of the gear there, and now they have to set up camp. So you can see there's a bathroom tent, there's a kitchen tent, there's a drill tent, and then communal sort of science tents. And here we're inside the drill tent, and we can actually see the ice core drill working. So the way it works is that you go down this hole, and you pull up about 3 feet of ice with every run. And so you can see the next 3 feet of ice coming up here, and that's what it looks like. It's about coffee can in diameter. And the ice is about 700 to 800 feet thick. And so we have to keep sending that drill down the same hole over and over and over again, getting the next 3 feet of ice deeper and deeper. We pack them into these insulated boxes so that the ice cores don't melt. We helicopter them down to base camp. We can see it right here. The ice core boxes get dropped by helicopter, and then we actually have to load them onto a ski plane, which takes them out to a freezer truck. And that freezer truck brings them all the way back to my Dartmouth lab, where we can actually analyze them and see the climate record that they preserve. So here's that same site on Mount Hunter. It's at 13,000 feet elevation. You can think of this as Dartmouth's Denali campus. And when we look at the ice cores from here, one of the things we can look at is times when in the afternoon on a particular day, it got really warm and the surface snow here actually melted a little bit. And so this is what that looks like. If you take one of these coffee can ice cores and you lay it on its side and you cut it in half, it looks something like this. And it's a little confusing, so I'll just walk you through what you're looking at. These darker sections of the core here, this is what we would call normal ice core. This is snow that's been compressed under the weight of the snow above it, and it has not been affected by any meltwater. It's not been melted and refrozen. Versus these lighter bands here, these represent those individual afternoons when it got really warm at the drill site, warm enough to melt the snow, and that meltwater trickled down a little bit into the underlying snow and then froze again. It refroze into these ice layers. And so you can see that this particular section of core, which probably represents a couple of months of time, there's a good number of these refrozen melt layers representing these warm afternoons. And we know through other analyses that this represents 2009. For comparison, I can show you what one of these ice cores looks like from a century and a half ago, from 1866. And we see there are no melt layers down at that depth, representing that period of time. And so we don't just do this for a couple layers here and a couple layers there. We can do this scientifically, very precisely, for every layer throughout the entire ice core. And this ice core stretches back hundreds and hundreds of years in time. And when you put all the data together, this is what you see. I'll walk you through this. On the left here is 1650 AD. So this is 350 some odd years ago on the left, and then today on the right. Each one of these colored dots in the top plot here represents one of those individual layers of refrozen melt layers. This represents one of those afternoons where it got hot enough to melt the snow at the drill site. You can see that there were a whole lot of them beginning around 1950, and they're getting more and more abundant. The color of these dots represents the thickness and intensity of those melt layers. And so if we go back just 150 so odd years, we can see that they're pretty unusual, and we go back even further and we don't see any of them. So what this is telling us is that there's a lot more melting today at the top of this mountain in Alaska than there used to be. In fact, when you quantify it, it's about 60 times more melting here than we used to see in the 1800s. And when we published this, this got a little bit of media coverage showing that this was the fastest that this glacier had been melting in at least 400 years. And it's not just this glacier. At Dartmouth, we take our students to various glaciers around the world. This is one where we go every fall. We take our junior undergraduate students to this glacier to study it and to learn how to do this kind of glacier research. This is called Athabasca Glacier. It's in Jasper National Park near Calgary. Some of you may have even been there. It's a super accessible glacier. It's an amazing place to visit. And this is what that glacier looked like in 2017. And so you can see here's a group of the students. We walk them up the whole glacier and take them to this first head wall where the glacier gets really broken up into crevasses, and it's not safe to go further than that. So this is what it looked like in 2017. And fortunately, we actually have images of what it looked like a century before this. And I've tried to line these up as perfectly as I can. So this is what it looked like in 1917, a century earlier. So here's 2017 and 1917. And I'll sort of toggle back and forth a little bit so you can just get the scale of how much this glacier has not just retreated in terms of backing up the valley, but how much it's also thinned down vertically. It's an enormous loss of volume. And we had an undergraduate student who studied this for her senior thesis and was able to determine that pretty much everything you can see in this picture here should be gone by 2060 based on the rate at which it's currently melting. And this is characteristic of literally every single alpine glacier in the entire world. There are a couple of outliers here or there, but every region of the world, we see the same process of alpine glaciers melting. These are the first canaries that respond to the warming. But if we're thinking about sea level rise, we don't just have to worry about the mountain glaciers. We really need to look to the elephants in the room, and that's the Greenland ice sheet and the ice sheets that are in Antarctica. There's two of them in Antarctica because they hold a lot more sea level potential than the mountain glaciers do. The mountain glaciers have about 3 to 5 feet of sea level total. Greenland has about 23 feet, and Antarctica combined has over 200 feet of sea level potential. And so we've done a lot of research in Greenland, and I'll focus on that here. For this expedition, we spent 2 field seasons, and we actually collected ice cores at each one of these red dots. So we collected a total of 16 ice cores, about half of them in year 1 and half in year 2. And in order to do this, we actually had to traverse across the ice sheet on snow machines, on snowmobiles. And so we were first dropped off here at Die 2, and we made our way in year 1. We made our way north, collecting all these ice cores, and then ended at Summit. And then in year 2, we got dropped off at Summit and made a big circle for this northern pass to get the rest of these ice cores. And so most of these cores, whereas that one in Alaska was about 700 feet long, most of these cores were about 100 feet long. So they don't go back quite as far in time. But the big question we were trying to ask is, how fast is Greenland melting today from modern warming? And just to give you a sense of what this actually looks like logistically, you can see the snowmobiles here. And basically, we need to carry with us everything. I already put it up outside. We need to carry everything with us that we might need for the next month. So this is not just all the scientific equipment, but it's all of our survival equipment. It's our cooking equipment. It's our camping equipment. It's our first aid equipment. These 2 little pods here are emergency shelters in case we get stuck in a really bad storm. Windstorms are really dangerous because they can tear your tents apart on the ice sheet. There's nowhere to sort of hide from a windstorm except down in the ice. Fortunately, we never had to use these sort of survival pods, but we had them just in case. And this is what our camps look like. So you saw the one in Denali. This is what our sort of Greenland campus looks like. These are our individual sleeping tents, and then our sort of communal kitchen tent. And you can see a bird's eye view. This is from a drone footage where you can see our communal tents are the big ones here. Here's our personal sleeping tents. And then we do our science upwind from the camp so that we don't contaminate the camp. Everything we do has to be super, super clean because this is some of the cleanest ice on the planet. So anything off our clothing or even our breath can contaminate our samples if we're not careful. And actually, this picture is a nice sort of summary of the various things that we have to deal with on these expeditions. This is a picture of me in Greenland. You can see our camp in the background. And one, you got to stay warm, right? You're on an ice sheet for 6 weeks at a time. Showering is not really possible. So you got to stay warm, but we also have to stay clean, as I said. So I'm wearing a full Tyvek suit here. This is a non-particulating suit that makes sure none of the fleece or lint or whatever that's on my clothing gets introduced to the samples. The other issue is that there are polar bears. This is their home, not ours. And we're required by the Greenland government to carry a rifle with us just in case of the worst case scenario of a polar bear coming into one of our tents and trying to attack us. Of course, that's extremely unlikely, has not happened to us, but we're required to have it. And you can see it slung over my shoulder here. So it's a strange combination, trying to stay warm, clean, and bear safe at the same time. And here you can see a couple of my graduate students. This is Karina and Gabe. You saw the drill on Denali. This was a smaller scale drilling operation where we are actually physically holding the drill. It's more like a really powerful hand drill that you might, get at Home Depot or something. And when we look at these cores and we do that same sort of melt layer analysis, we see a very similar story to what we saw on Denali, where we can go back hundreds of years in time. And this plot represents the amount of melt that we saw at these ice core sites. And we can see that in the last couple of decades, it's really increased dramatically. And what's interesting about this is that it's not just the fastest melting we've seen in several centuries. It's really struck me that that this increase has really only just started in the mid-90s. Throughout our research, 1995, 1996 keeps coming up as this critical time when we sort of transitioned into an obviously anthropogenic regime in the Arctic. And we might come back to that date again. So it's really just getting warmed up. It accelerated in the mid-90s. And what we think is that, the ice sheet is really responding in the mid-90s to temperatures that it was feeling earlier. These are huge ice sheets. It takes them a little while to actually respond to the climate change that it's experiencing. In contrast a bit with these much smaller mountain glaciers I showed you, where because they're smaller, they're able to respond much faster. And there's some concerns about Greenland because once you get it melting, it turns out it's pretty hard to stop it melting for three reasons. And each of these reasons are what we would call a positive feedback or a self-reinforcing cycle. And one of them is that when you melt the ice sheet, you actually physically lower the ice sheet. It gets lower. And as we know, as you go up in the atmosphere, if you climb a mountain, as you keep going up, it gets colder and colder, right? The atmosphere is colder higher up. So as the ice melts and lowers, it's actually lowering into warmer air. So the warm air makes it melt, and then it lowers into even warmer air, which makes more melting, and you can see how that's self-reinforcing. The other thing is that when you melt snow, it gets physically darker. And darker snow actually absorbs more sunlight. And we've all experienced this, right? Because you get a fresh snow event in the middle of winter and you go outside and the sun's out and it's completely blinding. And that's because like almost all of the sunlight that's coming in is getting reflected back off that fresh snow. But you go out a couple days later and that fresh snow has now been melted a little bit. There's some soot on it, some pollution has fallen on it, and the crystals have sort of reformed. All of a sudden you can be out there without sunglasses and you're just fine. So as it melts, it gets darker and then that makes it melt faster. And then the last thing is that once you start melting ice, you bring in liquid water. And when you mix liquid water with ice, things move quickly. This is something that we see over and over and over again. It is far easier to melt an ice sheet and to move it once you introduce liquid water than it is to grow an ice sheet. And I want to show you an example of this. It's sort of in miniature, but it was a pretty dramatic example for me, something that really changed my perspective on this. And this is an example from 2012. We were here in this region of Northwest Greenland in an area called Thule. This is near the Thule Air Force Base, actually. It's an old Cold War era Air Force base that's still active today. And we were there studying the glaciers and the lakes that are up against the glaciers. We had some lake scientists with us as well. And as we were flying into one of our campsites, we took this picture of this really big lake. This is about a mile in circumference that is right up against the ice sheet. And actually, you can see in this picture, it almost looks like it's sort of like overfilled a little bit. You can see a little bit of this lake ice that's supposed to be on the surface, and it's still attached to the ground, and it's actually underwater a little bit. And that's because at that time, 2012 was the hottest summer in this part of Greenland. And so there was a lot of meltwater coming off the glacier, filling up this lake kind of over the brim. So just to give you some perspective, that's the lake I just showed you in the circle. And we ended up camping at another lake further south. And because of the polar bears, we needed to have people up all night. Somebody had to be up all night. We would take turns on bear watch. And one morning we woke up and we were comparing notes over breakfast, and we all remarked that we heard this really weird noise in the middle of the night. Not a bear, but we heard like the sound of rushing water, like some new river that we didn't hear at the moment in breakfast and we hadn't heard the previous nights. So a couple of days later, we were actually flying from this camp up to a camp up here, flying right over this lake. And if this is what the lake looked like before on August 5th, this is what that lake looked like a week or so later when we went back over. The lake had actually catastrophically drained, probably in the span of several hours, certainly less than a day. And then when it catastrophically drains, the ice here collapsed down into this now empty lake basin. And it's a little tricky to get a sense of scale here. This is something on the order of 130 feet. And as I said, the whole lake basin is about a mile in circumference. And so this area that I'm circling here, where you can see the water right up against the hillside, that's this here. And you can see where the shoreline used to be. It's where the color change occurs in the brown. So that's where it was, and then this is where it is. And this is another perspective. What we think happened actually is the water was slowly tunneling its way under the ice sheet, and it was actually supporting some of the weight of the ice. And when the water eventually tunneled all the way to the ocean, which is just outside this picture here, the water catastrophically flowed out under the glacier and out to sea. And then not only did the lake drain, but this whole section of the ice sheet, woof, collapsed down. And again, it's hard to get a sense of scale. So I've got a helicopter video here that I think can help give you a little sense of scale. So here we're taking off from that northern campsite. You can see some of this area where the ice seems to have recently collapsed on the edge of the glacier, just beyond the lake. And then in a second here, as we rise back up, you'll see this empty lake basin and the collapsed ice sheet. So here it is. We're coming up on this collapsed basin now, and this big, canyon, these chasms that opened up when the ice sheet collapsed down. These are huge, right? It takes us a couple of minutes to fly around this whole thing in a helicopter. We actually walked right out to the edge here. It's a bit foolish. We didn't really know what we were dealing with at the time, but right out to the edge, this thing is massive. And this all happened in the span of a few hours. And in fact, we went back to this site. This was in 2012. We were there again in 2015, and it's still there. You can still see this whole feature. It's not going anywhere. This is such a big event. And in fact, I can still see it on satellite imagery today. So we just happened to be there during this catastrophic lake event. And it shows you what happens when you mix solid ice with liquid water. Things can happen catastrophically very quickly and unexpectedly. And so all this water from the melting ice is obviously raising sea level. Just to show you some of the data, sea level's gone up globally, global average, by about 8 inches. But the other thing to notice is that sea level rise is accelerating. So it was rising at about 1/4 of an inch per decade in the early 1900s. It doubled to 1/2 inch per decade through most of the 20th century. And now we're 3 times that at around 1.5 inches per decade for the last few decades. So this is accelerating. And as we look to the future, I mentioned our climate models are actually pretty darn good at this. What we don't know is just how much CO2 is actually going to be emitted by global society. And so we have different scenarios, high CO2 scenarios, mid and low. These low scenarios are in line with the Paris Accord. So those require pretty aggressive decreases in global emissions. The mid scenarios are sort of in the middle, and then the high are actually thankfully not really likely at all anymore. And I'll come back to that at the end. But what we see in all these models is the more CO2 you put in the atmosphere, the more warming you get and the bigger the impacts are. But I want to emphasize that there's a difference between temperatures and sea level. So if we look at sea level rise in the models, what we see is that sea level is going to keep going up no matter what we do for centuries and maybe even for thousands of years. As far as like human beings are concerned, sea level rise is a forever problem, okay? And I want you to contrast these curves that going out to 2100, even under Paris, sea level is still going up. And you can contrast that with temperature, where under Paris, temperatures are actually slowly coming down for the second half of the century. But that's not the case for sea level rise. And it's because, as I said, once you get the ice sheets melting, it's really hard to get them to stop. Now, there is some good news on this front. You'll see this unlikely but possible dotted line here, dashed line, which is really scary. 5, 6 feet of sea level rise by the end of the century. There's new research just coming out in the last year or two showing that it's really highly unlikely that we'll be up in this range. We're more likely to be down in this range, and as we look out to 2300, you might be up in that 5, 6 feet area, but you're unlikely to be up near the 10 foot. So these sort of worst case scenarios that are still out in the literature, this is in the latest IPCC report from a couple years ago. The latest research shows that they're actually very unlikely, and that's great news. But we do need to put in our head that this is different from temperature. It's different from storms, which are really related to temperature, that sea level is going to keep going up for thousands of years. Now, it might go up faster if we put more CO2 or slower if we put up less CO2. So I'm not saying that, that our activities don't matter for sea level. They absolutely matter for sea level rise. I'm just saying that we have to separate it from temperature in our minds No matter what, it's a forever problem that we need to deal with as a society. And we're already, of course, dealing with this as a society, not just during storms. This is so-called sunny day flooding. This is Miami Beach, almost a decade ago now. Miami's been dealing with this. This is just an unusually large high tide, and you've got significant parts of the city flooded. Same with Italy. Same with Annapolis. Same now with New Hampshire, right? You can go down to Hampton, New Hampshire, and during king tides, this is what it now looks like. This is not during a storm. This is just an unusual high tide. We've already lost about $15 million in real estate value on the New Hampshire seacoast alone. And you can then think about multiplying that up and down the entire eastern seaboard and then around the entire global coastline. But of course, when we notice sea level rise the most is actually during storms. This is when the storms and the winds actually make sea level higher temporarily for a few days. And so, for example, January 4th, this is in downtown Boston near the aquarium. It's now the #1 highest flood level. It was a 100-year flood, and these are billion-dollar events, right, in terms of total damage. 4.5 feet above the high tide level, breaking the record from the famous blizzard of '78. But increasingly, storms that didn't give us this #1 highest level are now giving us these levels because global sea levels are continuing to rise. And we can see that as we look out to the future. So here is a map of Boston showing the amount of flooding that happened in that 2018 nor'easter. And everything that's in light blue here was flooded. We can look at that exact same nor'easter and just add sea level rise to it to see what it would look like in about 50 years in 2070. Even under a lower Paris-like CO2 estimate, that exact same nor'easter causes this much flooding, right? You can see the difference between this, which is a billion-dollar disaster, and you can imagine how you scale the damages with something like this in downtown Boston, where if you've been to Boston recently, this is all newly developed. Seaport, tons of stuff going in here, lots of stuff going in here through the southern part of downtown and across the way up into Charlestown and everything further north. So this is all areas that's being actively developed. So let's talk a little bit more about the storms, and this will take us to talking about the jet stream. So we were looking at that nor'easter. And that nor'easter is sort of characteristic of this pattern that we've seen. We all saw the flooding last week, right, from those catastrophic storms. We had this same kind of catastrophic storms a year ago, the flooding in 2023 July, and then the floodings that have happened in the years before, often in July. And so our research group has been digging into this. This was led by a graduate student named Wanping Wang. Going back to around 2016, he started working on this. And what we found is that if you look at rainfall, and you take the most extreme rainfall events, these are the biggest rainfall events that happen like once or twice a year. The ones that give you like 2 to 3 inches of rain, right? The ones like we had a week ago. If we look at just those biggest rainstorm events, we see that there was a big jump in how much rain they delivered, again, right back here in around 1995, 1996, this critical time where we sort of jumped into this new anthropogenic climate, at least in this region and up in the Arctic. And it was actually a 50% jump in the amount of rain that those storms were delivering. And as I said, we all know what I'm talking about here. Like Woodstock, more than perhaps anyone, understands what we're talking about here. This is Hurricane Irene, and this is those nor'easters. And so what we did was try to figure out, okay, what actually caused this jump, this 50% jump? Is it hurricanes? Is it nor'easters? Is it thunderstorms? And it turns out it was all of them. It turns out about half of that jump in extreme rainfall was due to hurricanes like Irene. 50% could be attributed to more rainfall in this area associated with hurricanes, and Irene is the poster child for that. We've also seen this, of course, around the country. Hurricane Harvey in 2017, $131 billion. And what's really interesting is now we have the capability in the climate science community to see what would Hurricane Harvey have been like without human CO2. And how much more likely was Hurricane Harvey because of human CO2? We didn't used to be able to do that. But just in the last 5-6 years or so, we've been able to actually make these analyses and put numbers, real numbers to this. And so what researchers found is that Hurricane Harvey was actually 3 times more likely because of human CO2. and that human CO2 increased the rainfall by about 15 to 20%. And what you'll see now with these big storms that happened recently, there are research groups that can turn around these analyses almost overnight. And if you know where to look, you can find these kinds of statistics for pretty much every major storm we have. But it wasn't just the hurricanes that have been affecting us. As we know, it's these other storms too. And it's not just your imagination. The data supports it. That since around 1995, about half, 40% of that jump that we've seen is related to these thunderstorms and nor'easters. And so again, July 1st in particular, like careful on July 1st around here. July 2013, 17, last year, this year, we get these big events that have really strongly impacted our communities. And so these events are associated with the jet stream. We know that when the jet stream is wavier, like this orange jet stream here, when the jet stream is wavier, you tend to get more thunderstorms, you tend to get more nor'easters, and they tend to be more powerful. And that's because when the jet stream is wavy like this, you're more actively mixing really warm, moist air from down south with this really dry air from the north. And in meteorology, that's how you make things happen, is you mix two different air masses with different densities and you push them together. And so this wavy jet stream is really good at making the storms more intense, in contrast with this sort of less wavy jet stream shown in red. So we know that a wavier jet stream is associated with these storms. And so it makes sense to ask, like, is the jet stream getting wavier? And there's been this really interesting line of research that has come out saying, yes, the jet stream is getting wavier, and that wavier jet stream is tied to the warming Arctic. And so what I'm showing in this map is the amount of warming over the past century or so across the globe. And what you can see is that there's darker reds here. There's more warming in the Arctic than the rest of the globe. We call this Arctic amplification, okay? And this makes sense because areas that have ice, like the Arctic, when you start melting that ice, you can increase the temperature really quickly, right? You're not just warming up the air temperature, you're warming up the air temperature and reducing the ice, and that makes the air warm up even faster. So it's, again, one of these positive feedbacks, these self-reinforcing cycles. And you can see it clearly in the data. This is very well established in the science that the Arctic is warming about 2 to 3 times faster than the rest of the globe. And so there's this hypothesis out there that as the Arctic warms faster, what you do is you make the jet stream wavier. And the way that works is that the jet stream is caused by a temperature gradient, the temperature difference between the Arctic and, say, the equator. And if there's a bigger difference between them, you have a steeper slope here that makes for a more powerful jet stream. And a more powerful jet stream tends to be less wavy. And you can think of this intuitively if you imagine a cowgirl with a lasso, right? And if they move that lasso really, really quickly over their head, it's going to be nice and flat in a nice perfect circle. And if they do it slowly, you're going to get big waves in the lasso, right? It's the exact same thing with the jet stream. As the jet stream goes faster, it tends to flatten out. And as it goes slower, it tends to get wavier. And so the idea is, as the Arctic warms more than the equator, you have smaller difference between them, a smaller gradient. That means the winds are weaker, and that makes the jet stream wavier. That's the idea. And this has gotten a lot of attention, both in the scientific press and in the public press. Big years like 2011, where we had a really wavy jet stream and we had 2 feet of snow in New York and we had blizzards in DC. This is one of my all-time favorite pictures, the 2 feet of snow. And people have been linking these Arctic warming with the more extreme weather that we see in the US. This also gets a lot of press because meteorologists seem to really love to use the term polar vortex. They just love it. Polar vortex, polar vortex. So you hear it all the time. And that is, again, associated with the jet stream. It's when the jet stream is wavy, you get these big polar vortex events. You may remember the famous Texas ice storm and power outage from 2021 that, again, in the media directly linked with climate change. And it's, again, through the jet stream. And one of the more interesting and unusual things I've seen in the media about this is that when you get these really wavy jet streams and you get a polar vortex event in Florida, the iguanas fall out of the trees because they kind of hibernate and they get by the cold. So you got to be careful in Florida with the falling iguanas. So our research group wanted to dig into this, and in particular, your very own Jacob Chaliff. He's the treasurer of Sustainable Woodstock. He was an undergraduate student at Dartmouth when he decided to dig into this, first for a class project and then for his senior thesis. And he actually just submitted this for publication last week. So this is like hot off the presses scientific research here. And what I'm showing here is a metric of jet stream waviness. And on this plot, up means more wavy jet stream and down means a less wavy jet stream. And most of the research that's already been done on this has only gone back to around 1980. And when you look at the recent jet stream in the last couple of decades and you compare it to the record going back to 1980, you can see why people are like, yeah, the jet stream is pretty wavy right now. But Jacob wanted to ask, like, is today's jet stream actually all that wavy? And so what he did was he extended this record back all the way to 1900 using different data sets than people have used before. And what he found is, no, not really. There are lots of times in the previous century where the jet stream was as wavy, if not more wavy, than it is today. And importantly, Arctic amplification really only started around 1980 or so, maybe even more like 1990. So all these events back here where the jet stream was super wavy, we cannot attribute that to Arctic amplification. So this research is going to be a little controversial when it comes out, which is the best kind of research. But I would say the jury is now out after this sort of decade of people talking about jet stream waviness. We'll see how this paper lands, but I think my mind has been changed on this. All right, last two slides. I just want to give you a little sense of why I'm optimistic that we are actually making progress and we can actually work towards a better future, and that we already are. So I showed you these different CO2 scenarios with the climate models. What I'm showing now is what CO2 emissions look like under those different scenarios. And starting today, moving out to the end of the century. And so this is what we call the high CO2 scenarios. These are the mid scenarios, and these are those low scenarios where we actually start dropping emissions immediately. These are still called quote unquote business as usual scenarios. And it is not business as usual anymore. We are no longer on this path at all, thankfully. Back in the 90s, we were. We are not anymore, and that reflects real progress in global emission reduction. You can see that with current policies, we're actually more in these sort of mid CO2 scenarios, and with pledges, we're even lower than that. We're not down to the Paris levels yet, but we've made a lot of progress. And I'll also say that personally, when I hear narratives about, we only have 5 years to act before it's too late, or 2 years before it's too late, personally, I don't think there's any such thing as too late for planet Earth. I've got kids. I hope that they have kids. Is there ever any such thing as too late for your kids? Not in my mind, right? So I really focus, particularly with my students, on how we can move forward rather than getting super depressed about our situation. I really worry about hopelessness. And I don't think it's hopeless. We've made good progress. We can make more. And as an example of this, we can see what just one piece of legislation did, the Inflation Reduction Act. So this is showing just US greenhouse gas emissions. A lot of people don't know that US emissions have actually been dropping since around 2007. And so we've been on this slow decline, not fast enough. And when the current administration took office, this is where we would have continued by 2035, is this top black line. The infrastructure bill that they passed did a little bit to reduce CO2. They wanted to Build Back Better. Remember that $3 trillion plan? Couldn't get that through Congress, but they did get the IRA through Congress. And the IRA had almost all the climate legislation in it that BBB did, almost all of it. And you can see what a huge chunk of this pie we were able to take out with one congressional act. We're not down to where we need to be to reach Paris, but it was a really big step in the right direction, and that needs to be celebrated and needs to be doubled down on. We can do this. We need to do more. So my take-home message is sea level rise is a forever problem. We are seeing more extreme rainfall. It is not your imagination. But in terms of the connection with the jet stream, and particularly the connection with Arctic warming, I would say the jury is out. And then we are making progress towards net zero, and we need to do better. We need to accelerate, but I also think we need to be careful about hopelessness. And I'm happy to take any questions y'all might have.
Lovely. Thank you so much, Eric. So everyone, the questions will be taken through the chat. So if you haven't used Zoom chat before, if you go to the bottom of your Zoom screen, there will either be a chat button or you can click on the More button and the chat will be under that menu that pops up.
And I literally have 216 slides in this deck. I only showed you a small portion of them. So you can ask me, doesn't just have to be about this. If you got some burning climate question, feel free to ask. If I don't know the answer, I'll tell you. I might just have a slide on it.
All right, looks like our first question is, what are the pledges on the one slide?
Yeah, so these are when countries, usually through these international agreements, will make pledges for these announcements, but there's not necessarily legislation that has been passed in that country to force them to actually live up to that pledge, right? So the orange here is what has actually been passed in legislation. These are policies. The pledges are usually more ambitious than that, and it's often a little bit of a delay before various legislatures in countries around the world can catch up with what the pledges are.
All right, anyone have any other questions? Oh, here we go. So from Lori, I wondered about the day after tomorrow and how the Atlantic current plays into this scenario. The New York Times recently had a front page notice about the slowing of the Atlantic current.
Yeah, that's an awesome question. So, like many things in Hollywood, it is based on a kernel of truth, and it is, besides that kernel of truth, completely wrong. The Hollywood movie is. So the kernel of truth is that, yes, as the New York Times says, the Gulf Stream is slowing down. And one way that we know that is one of the only places in the whole world that's not actually warming right now is this area just south of Greenland. And that's because this area of the ocean gets warmed by the Gulf Stream. The Gulf Stream brings warm water from the Gulf of Mexico right up to that spot. And if you slow down that conveyor belt of warm water, this area cools off. And sure enough, it is. So it's actually really hard to measure how fast an ocean current is moving, but we have very good evidence scientifically that the Gulf Stream is slowing down. And it's slowing down most likely because all this fresh water coming in off these melting glaciers and all the fresh water coming through the rivers from all this extra rain are freshening the surface ocean here. And when you freshen the surface ocean, that causes the Gulf Stream to slow down. So that part is the nugget of truth. Are we worried about any sort of day after tomorrow scenario with the slowdown of this? No. What I am worried about is that as you slow down the Gulf Stream, you actually increase local sea level rise on the eastern seaboard of the United States. So the eastern seaboard of the United States, it turns out, is a hot spot for sea level rise. So it's sea level here is rising almost twice as fast as the global average. And partly it's because the Gulf Stream is slowing down. When the Gulf Stream slows down, the water kind of sloshes against the coastline a little bit more. So I worry about it for that reason. Actually, in terms of temperature, slowing down the Gulf Stream might help Northern Europe a little bit, not warm up quite as much. In my paleoclimate world, looking deep back into the last ice age, we know that the ocean circulation can really shut down. And we don't expect that to happen. We do expect it to slow down and to continue to slow down into the future, but it's really sea level rise that I think about it more than anything else. Yeah, you can see here's the accounting for it. So global sea level rise is like 20 inches. This area of the land is actually sinking because we're pulling out so much groundwater for the megalopolis from DC to New York and Boston. And then the ocean currents add another 8 inches. So that ocean currents specifically refers to the slowdown of the Gulf Stream. And so you end up with a total of about twice as much sea level rise in the mid-Atlantic region as you do global average.
Wow. Our next question is, how often are ice core samples collected in Denali and in Greenland?
Yeah, so different answers for those two spots. Denali, basically our group, and when I say our group, I don't just mean Dartmouth. We work with researchers at the University of Maine, New Hampshire, University of Washington, in the USGS. We have this core research group of about 20 or 30 people. Our research group is pretty much the only folks collecting ice cores now in Denali. And so we try to go every year. We collect an ice core every few years to try and update the record. We will probably never go back and drill a deep ice core there again. And so part of what we do when we drill these cores is that we keep about half of it safe so that other researchers can analyze it. In Greenland, there is a lot more research. It's a much bigger place. There are Danish researchers are super active in Greenland, other European researchers, and lots of different US research groups. So every summer, there are, I mean, I'm just guessing, somewhere around 20 plus different research groups, somewhere around Greenland, collecting snow and ice samples in different parts.
We've got a really sweet message here. Your presentation was impressive. Thank you so much for what you're doing. Very grateful for the message of never too late. Hopelessness is not good.
Oh,
Meanwhile, we still have much to do.
We do. We do.
My 20-something kiddos are quite pessimistic that anything individuals do will make a difference. Do you have any suggestions on talking points that will increase their climate healing hopefulness?
The way I approach it is, and this is just my personal opinion, the way my family, my wife and I have approached this is that we're constantly asking ourselves, like, one way to frame it, what is ours to do, right? I can't solve all the world's problems. None of us can solve all the world's problems. We certainly can't solve global warming on our own. So what is mine to do? For example, our car died a year ago. We needed to get a new car. I was like, you know what? Let's go for a plug-in hybrid because sort of the best of both worlds. I don't know about the charging infrastructure yet. My wife was like, let's go all in, Eric. Let's go EV. And I love it that she pushed us there. Would love it. It's amazing. We just installed heat pumps about 3 weeks ago in our own house. That was something we couldn't afford to do a few years ago. We're now in a financial position where we can do that. I understand that, like, what is mine to do has different answers for every single person. What's yours to do might be just volunteering or doing some cleanup or just talking with people about these issues. For different people, it looks different ways. But what we're constantly asking ourselves is, okay, what's next for us? What's the next thing that we can do? Part of what's mine to do is things like this, is trying to get the message out about the work that I do, the science that I do, and try and talk about it in a way so that other people can understand it. So again, the answer to that question, what's mine to do, is constantly changing, and I think it should. But that's how I approach it. And in terms of, does one individual action, there are so many different examples of how thinking like that can lead down less hopeful roads, right? Saving one individual dollar doesn't help you, but you start saving individual dollars and all of a sudden you're saving real money. One individual vote isn't going to determine an election most of the time, but if everyone felt that way, our democracy would fall apart, right? So all these kinds of examples of individual actions, when you pull them all together, make an enormous difference. And all you have to do is look at the progress we've made. We really are making progress. We need to accelerate it, but we can take hope in the progress we've made.
Thank you. From Peggy, have humans evolved at all to handle higher temperatures, and how long does adaptation take? That's a fun question.
It's a really great question. And most of my work locally is focused on adaptation, not so much at the sort of human physiological level that I think Peggy is asking about here, but in general, as we know, we're already experiencing climate changes and we need to adapt to reduce the impacts. I don't have a great answer for how long does it take the human body uh, to adapt. In terms of evolution, no. Our species, I'm trying to find the slide that I have that shows this nicely, but our species has only been around for about 300,000 years, and we've had about 3 ice ages, and we've had very little time on this planet when it's been as warm as this. So evolutionarily speaking, our species hasn't experienced much like this before. Um, but yeah, here you get a sense of it. Okay, so we show up as a species somewhere around here, and this is temperature, right? So here's an ice age, here's another ice age, here's another ice age. But the places that we're heading temperature-wise are sort of uncharted territory, and there are physiological limits to what humans can endure. And so when you look at particularly regions around the equator in the tropics, and you look at extremes, right? The hottest days near the tropics under these scenarios, uh, there are days when it's just physiologically challenging for humans to survive. And that sounds really extreme. Those days already happen, and humans are able to survive in those environments through various adaptation measures. And also, heat is one of our number 1 killers. I think people generally think about storms, but even in the United States, heat heat kills. So while we don't, I always want to be careful about exaggeration or certainly hyperbole. There are physiological limits to human tolerance, and we have the ability to develop techniques, methods, strategies to adapt.
David asks, do you have an opinion on the concept of introducing chemicals into the atmosphere to make it more reflective?
I do. I think it's a sad state of affairs when that's what we're talking about. One of the success stories of the environmental movement is that we've been able to clean up our air dramatically, at least in the United States and Europe. Now we're starting to see it in Asia. Air pollution, which kills millions of people every year, air pollution has been dramatically improved since the Clean Air Act and its counterparts. So the idea of putting more sulfur into the atmosphere, which was one of the things we cleaned up to get rid of acid rain and improve human health, in order to reflect, there's a really good science for it. We know when you have a big volcanic eruption that's what happens. But I would think that would be a last case, sort of worst case scenario, or a last solution we would look to. That being said, I do think that we have to start sucking CO2 out of the atmosphere. Like, we have to get to that point. We have the technological capability. It's not just about reducing what goes up into the atmosphere, our emissions. We have to get to a place where we suck it out. And like I say, this technology is in its infancy, but it exists. It does work. People are working on it. It's going to be huge business in the next several decades to maybe century. But I do think that will be part of the future. And I separate that from these sort of geoengineering natural schemes like putting sulfate into the atmosphere. I think pulling CO2 out of the atmosphere, turning it into concrete, putting it down into the ground in places like Iceland or other, geologically appropriate places. I mean, that's where the carbon came from. We pulled it out of the ground. It was happy there for millions and millions of years until we pulled it out. You can put it back down there. And once you get it back in the ground, it doesn't warm the planet. So I think that is where we're going.
We'll take one last question here. This is from Scott. Hi, I just returned from a research expedition to Svalbard. Svalbard? Am I saying that correctly? And points north of the 80th. PNAS just published a piece on the dominant role of CC on lengthening days. How might this impact the current climate models?
On lengthening days. I'm not quite sure what Scott means by lengthening days. Dominant role of climate change on lengthening days. Can you clarify, Scott? Oh, melting sea ice is causing the planet to rotate slower. Boom. Wow, that's amazing. Yeah, I had not. That's a new one for me. I had not read that yet. I had not heard about that yet. It certainly makes sense. My guess would be, this is just a guess, knowing nothing about it. My guess would be that the effects of that would be minor enough to be noise in the data, but I could be wrong. That would be really interesting to understand. I mean, presumably you would see a much bigger signal of that with the ice age cycles, the glacier interglacial cycles. And so it'd be cool to run climate models looking, say, at like how the length of day changed with the last glacial maximum. And just for a reference, we're talking 5 or 6 feet of sea level rise in the future. During the last ice age, sea level was 300 feet lower, right? So 5, 6 feet versus 300 feet. So we could whack the Earth with an ice age in a climate model and see what that does to the length of day. That might be one way to check it out. But thank you so much, Scott, for you blew my mind. That's a new one for me.
It looks like Peggy shared something in
Yeah,
the
thanks,
chat
Peggy.
related. Thank you, Peggy. Well, great. Thank you so much for joining us, Eric. That was really interesting. And everyone, our next event will be a film screening of the film Common Ground. And the screening begins next week on the 24th. It's a really fun film, really positive. So I hope you can join us for that. And thank you so much again, Eric.
Thank you all. Appreciate you joining us. Have a great night.
You too. Good night, everybody.
Thank you.